All right. So we've been talking about sums of indicators, right? And various sorts of sums. And in fact, I'm having you work through sums of uniforms right now. But, sums of indicators can make our lives a lot easier in terms of computation and whatnot. So one example that I think is really pretty helpful, and I was gonna kind of touch on this on the next lecture, but right now is as good a time as any, I guess, is the so-called coupon collector problem. Okay, so the coupon collector problem is kind of interesting. What you do is you basically say, uh, all right, I'm gonna imagine that I have a bunch of things that I'm collecting out of like cereal boxes or something. They used to put little prizes in cereal boxes or Cracker Jack boxes, and you were interested in like collecting these things. Now, the reality is some of the prizes were generally rarer than others, but the goal was to like get them all, okay? And but in the coupon collector problem in its most elementary form, you just assume that any box is equally likely to have any one of like the prizes that you're looking for. Okay, so let's suppose, so this is, oh man, I'm sorry guys, I'm gonna have to log into the thing here. I'm sitting here writing and my thing isn't even uh, in the screen yet. So hang on. There we go. Close. Stop that. Share the content. There we go. Okay, so this is the so-called coupon collector. Oops. Coupon collector problem. Okay, so we have like, let's say capital N distinct coupons. I like to think of them as prizes because that's a little bit more exciting. And each box has one prize, and each prize is equally likely to occur, equally likely to be present, I guess is how we would say this. Okay, so so the probability of any given prize is just 1 over n. Okay, so the probability of any given prize, that is if you purchase a box, is just 1 over n. Okay, so here's kind of the question. The question is, how long do we expect to have to wait before we get all the prizes? Okay, so the question is, how many, right? And by the way, how long? I mean, a probabilist always thinks of that as the number of things, the number of purchases you have to make before you get them all, right? I mean, in theory, you could say, well, it's how long? It's going to take, 1,000,000 years because I'm never going to buy a box of that cereal or something, right? Or it's going to take infinity amount of time. But we're just assuming by how long we're thinking how many boxes do we have to purchase? So how many boxes do we expect to purchase before we have all prizes? Before we have all prizes. Okay? Well, that sounds like an expected value type question. Okay, so let's have a look at that. So let's just let X equal to the number of boxes purchased until all prizes are obtained. Okay, then what we want is we just want the expected value of X. Okay. Okay. And we're doing this kind of in the context of these sums of various things. Okay. So, I mean, what do you guys think? I don't want to like give away the farm here. If indeed you could sort of say, hey, why don't we just write it as a sum of these kinds of things or something? So what do you guys think? Can you guys think of a way that we could write X as a sum of simpler random variables that might be helpful in this context? Okay, so let me just say, can we write X as a sum of simpler random variables that are kind of easier for us to understand? What do you guys think? What do you think? Any ideas? So here's a hint. Let's let X1 equal to the number of boxes until the first prize. Okay. Until the first prize. Guess what? What's X equal to? Right? The probability that X1 equals 1 is equal to 1. You understand? So the expected value of X1 is 1. Yes? That's easy. Okay? Is there something that we could define X2 as? So like, what could we define X2 as? So think about it. So we purchase a first box, we have our first prize. Is there something we could define X2 as that might be helpful? Well, how about this? The number of additional boxes purchased after the first prize is obtained. After the first prize is obtained until a second new prize. Because in theory, couldn't I just buy, I have my first prize, yes? Couldn't I just, if in theory, I guess I could just keep buying boxes and keep getting prize number 1. That would be annoying, right? And I would want to somehow keep track of, okay, I keep getting these prize 1s, but then eventually I get a new prize, and I call that like my second new prize, okay? So does this make sense? X2 is the number of additional boxes I have to purchase beyond that first one, before I get a second new prize. What is the distribution of x2? What's the distribution of x2? What do you guys think? Matthew, were you about to say something?
Is it geometric?
Yeah, it's geometric. With what parameter? What's the
Success is not getting whatever prize you got first, which I guess would be 1
success
minus
is just not
1
getting
over.
that first prize, yeah? Okay. So what's the probability of not getting that first prize?
Would that be 1 minus 1 over n?
Yeah. Yeah, that's exactly right. 1 minus 1 over n. Another way to say that would be capital N minus 1 over little n. Okay. That makes sense? Yeah? Okay. So that thing is geometric. Okay. And the proportion of success is just capital N minus 1 over n. Okay. What do you think you would have for the third thing? How would you define the third thing? Somebody want to take a shot? What do you think 3 is going to be?
Additional boxes until a third new prize.
The number of additional boxes, the number of additional boxes after prize number 1 and 2 are obtained until we get what? Well, a third new prize. Yeah? And what's the distribution of x3?
Is that also going to be geometric with
Yeah,
parameter
geometric with what parameter, Katie?
n minus 2 over n?
Yeah, n minus 2, capital N minus 2 over n, yes? And how do you think we're going to define xi? It's going to be the number of additional boxes after prizes 1, 2, ... I minus 1, right? And these could be any, they're just distinct prizes. After distinct prizes 1 through I minus 1 are obtained until we get a new ith prize. Okay. So there's nothing special about one of these being prize number 1. It's just the one I happen to get first. The second prize is the second new prize that I got, yes? Then the third, etc. Okay. And what is the distribution of xi going to be?
Equals n minus I plus 1 over n.
Yeah. Okay. And so I have these random variables. I have x1, x2, x3, ... I think I even have x capital N, yes? And what's the relationship between x and these x's? Right, remember x was the total number of boxes. What's the relationship between x and these other things? It's the sum. Yeah? It is the sum of those things. Therefore, look, if we want the expected value of x, this is going to be the expected value of this sum. Okay. And by the way, even x1, let me just put a little note right here. Note, x1 was also stupidly a geometric, but it was really stupid geometric. You understand? What geometric was it? It was geometric with proportion of success equal to
1.
1, right? And I could write it as n over n even, which is 1. So that even obeyed the pattern that we've been dealing with, right? Namely that xi is always geometric with proportion of success n minus I plus 1 over n. Okay? That even works for I equal to 1. Do you see it? If I plug in I equal to 1, I get exactly the original thing. Yes? Okay? And now I can just add up these things. Okay? So this is going to be the expected value of x1 plus the expected value of x2 plus ... plus the expected value of x capital N. Now let me ask you. Okay, so what is the expected value of x1? We already computed it, didn't we? Right? It was 1. But I'm going to write that in a funny way. I'm going to write that as n over n. Okay. What is the expected value of? What's the expected value of any geometric, right? So if I want the expected value of any geometric with proportion of success p, what was that? Do you remember? Remember what that was?
Was it 1 over p?
Yep,
Oh.
1 over p. Yep. Okay, so the next one, expected value of x2, the proportion of success was n minus 1 over n. So this is going to be n over n minus 1. Next would be the expected value of x3, which is n over n minus 2, plus ... plus the expected value of n. What's that going to be? N over, what's that one going to be? N over capital N minus n plus 1. That's just n over 1. Yeah? And what do you see we can factor out of this thing? N. And if I factor out n, I see that what's left is it's just going to be 1 over 1 plus 1 over 2 plus 1 over 3, right? I'll write it in the opposite order. This is just 1 plus a half plus a third plus ... plus 1 over n. Okay? That's really interesting. So this is n times, like this right here is like the harmonic sum. Okay? I don't know if you remember or not, but this thing right here is really, really close to the natural logarithm of n. Okay? You can kind of see that by estimating it by an integral. So that means that the expected length of time that we're going to have to wait is basically n times the natural logarithm of n. And one thing I'll probably do, I mean, I'm not going to repeat all of this in the lecture for Friday, but one thing I'll do is I'll kind of justify this estimate right here. It's a very important estimate. Anybody who works in probability long enough, the minute they see this sum right here, which is like the partial sum for the harmonic series, yes? Right, that famous series that we use for all kinds of examples in Calculus 2 and in all of mathematics. That thing behaves like the natural logarithm of the last, of the denominator of the last term, okay? So one thing I will do is I will probably justify that estimate. But that's kind of interesting. I mean, you know, logarithm of n is much, much smaller than n. So on average, we expect to have to purchase, you know, n times the logarithm of n many boxes, where n is the number of prizes we're seeking, okay? And there's all kinds of like tweaks to this problem where, for instance, you might say, okay, I mean, my kids buy these stupid Hatchimal things all the time, okay? They just waste all their money on these Hatchimals, okay? You know what those things are? Hatchimals. Okay, they're called Hatchimals. You could go look them up, okay? Hatchimals. I guess it's supposed to look like animals, but it's Hatchimals. You go buy them and they're like these eggs, and you don't know what's going to be in the egg. And you like kind of warm up the egg with your finger or your hand or something, and the egg hatches and you get this little animal in there. And there's like hundreds of these things, okay? But they're not all equally likely to show up. There's like ones that they say are really rare. So they're always trying to get these rare ones, okay? So there are lots of versions. I mean, so they're playing the coupon collector problem. This is actually affecting my family right now, okay? They're actually going through the coupon collector problem in full force. And they're wanting to know, okay, oh man, I have to get that silver winged unicorn. That thing is like super rare, right? And so they're spending their money on these things. So in that case, though, you have different probabilities assigned to each one of those Hatchimals, okay? And it turns out that you can actually deal with the coupon collector problem in that setting also. You just have to be a little bit more careful. All right? Okay, I think I'm just gonna leave it at that for now. I will you know, at least revisit this in the lecture on Friday, but I thought that would be a nice thing to work through. So now you can go spend some time looking up Hatchimals on the internet, okay? Have a good time with that. There's also some other things called nom noms. You ever heard of that? Okay, they're called nom noms. Or I don't know, maybe num nums or something. But they're actually, you get these little cereal bowls, okay? And there's these little, they look like giant trick, you know, Cocoa Puffs or something. And you put milk on there, but it's not really milk, it's just water. You pour water on there, and then the cereal that they're embedded in starts to dissolve, and these animals kind of emerge in your you don't eat them, but it's almost like you have a bowl of cereal and they emerge out of there, and some of them are rarer than others as well. This is like the new thing with kids. They want you to have to keep going and purchasing more of these things because there's randomness invoked there, which I think is kind of interesting in some ways, but I just hate that I'm having to pay money for this sort of thing. It's their money, but it's really my money, right? I gave it to them, and then they go and they spend it on that. Okay, so the coupon collector problem is closer to my heart right now than it has been my whole life. Okay. All right. Well, I am going to stop right there. You guys have any questions on that? Any questions? Any questions? Any other questions? Oh, that's myself. I was like, who's this non-video participant? That was me, actually. Okay. All right. Well, I think I'm going to leave it at that. Hopefully that's sort of helpful. In that case, I wasn't using indicators, right? I was using geometrics to kind of get what we needed. I think that there might have been an exercise in chapter 7 that was sort of like that. Was that true? Matthew, I vaguely recall you asking me a question about that at some point. Was that
Are
true?
you talking about the bug problem?
Was that the bug problem?
We used the geometrics for the bug problem, but
Okay.
it was a little different because we were waiting until we got a specific bug. So
Okay. Yeah. So we wrote the sum differently. There we were waiting for a specific bug, whereas here we just said we're waiting for a new one, right?
yeah.
Yeah. So that's a little bit different. Okay. All right. I'll let you guys get back to whatever it is you have going on then. If there's no other questions. All right. Hey,
Thank you.
yep. Enjoy your day. See ya.
Bye.